Hello and welcome to the final video of our week on measurements, mapping, and modeling of meteorological phenomena. We'll be talking about radar and satellites, two very, very important tools when it comes to severe and hazardous weather. So why do we need remote sensing? And I've alluded to this previous to this video, but are in situ or are in place, the things where we actually have sensors stuck into the air, either at the surface or we send a balloon up through the atmosphere, or sometimes even we take airplane measurements or whatever it is where we're directly measuring the atmosphere. They just simply are too sparse. We don't have enough of them in space, and we especially do not have enough of them in time. So we need to have tools that have a lot better temporal resolution, especially. We have real-time data always coming in order to have good short-term forecasting. And extra spatial resolution, seeing things on better spatial scales, is always a plus as well. So our apologize for the thing driving across the road. Two primary tools for this are Doppler radar and satellites. And again, I want to emphasize how important these are in understanding severe and hazardous weather. Wanted to leave this one to the last, sort of leave the best for last in this week. You'll be seeing a lot of different satellite and radar images in this later portion of the course when we talk about severe thunderstorms and tornadoes and hurricanes. You'll be seeing these things a lot. So let's get into it. So radar originally comes from the acronym Radio Detection and Ranging, but it's been used so much in the century since its invention that it's lost its acronym status. It's just a term on its own now as a radar. And it consists of using directed radio waves in a pulse to detect objects that naturally act to scatter radio waves. So not all objects scatter radio waves equally. There's a reason why when we talk about aviation radars that there's stealth technology in an attempt to not scatter radio waves back to the radar. But when it comes to weather radars, what we care about are hydrometeors. Essentially, that's the fancy scientific term for water things in the sky. So cloud droplets, ice particles, snow, graupel, hail, rain, whatever. If it's water and it's big enough to be detected by these microwave frequency radio waves and scatter that radiation back to the radar, it's a hydrometeor that we care about, and we try measuring it with radar. But those same frequencies also pick up on other things too. So insects and birds, and if there's enough refraction based on the temperature profile of the atmosphere, refraction, the same idea like you have a prism of light. This is radio waves are electromagnetic radiation. They will refract in similar ways, just depends on the medium and the frequency response. But in the atmosphere, we have to deal with refraction as well of these radio waves. And so if that refraction is strong enough, you can actually bend the beams back to the surface, and then the reflection will similarly be refracted back to the site. And you can pick up things that are close to the surface, like wind farms and the ground itself. And sometimes you even see vehicles on highways showing up on your Doppler velocities that we'll get to in a bit. And there's sort of three physical things that the radar is picking up on that translates to important properties of what we're trying to detect. So the time it takes for this pulse to get to this thing, to get to the object, could just call it a thing, to get to whatever it is and to make it back, that is always a function. That time is something we can detect, but then we translate it to a distance because this is electromagnetic radiation. It's traveling at the speed of light. So we get distance from time. There's also an intensity of this reflected pulse. So there's a certain energy that is transmitted at, and it'll reflect or refract back, and we can use that to have a indication of the intensity. It's a very complicated function. If you want to take a course on radar meteorology, You can learn all about the radar equation, but in general, what you need to know for this class's purposes is that intensity is controlled by the size, the shape, and the type of the object. These all factor into that intensity return. But the biggest thing that matters is the size in the orientation of the pulse. So our primary radar pulses are usually horizontally polarized or oriented pulses. So the main thing we're detecting with intensity when we get back is the horizontal size of the objects that we're scanning. Finally, we also can pick up on frequency changes based on the behavior of these pulses as they come back and how their phases interact. But that frequency change is related to the speed of an object towards or away from the radar. Hopefully all of you are familiar with the Doppler effect. If not, look up YouTube videos on Doppler effect. It's very entertaining. You oftentimes can experience it with sound waves, because as something is coming towards you, the pitch or the frequency of the sound will be increased. As it's going away from you, it'll be decreased. So even though, say, a train's horn is blaring at a constant pitch, it'll be high pitch, high pitch, high pitch, and then shift to really low pitch as it goes past you. The same sort of thing happens with electromagnetic radiation, just you can't hear it, but you can detect it with your instruments. So these are the main things that we're doing. We know distance to object, some function of its size and shape, as well as its speed towards and away from the radar. So getting to that intensity idea, we want to construct fields of this. So to know distance, we have this 1D beam with distance. So the radar can sweep around in this way and tilt up and down in order to construct sort of a semi-cone, or that kind of an idea of a scan going all over in that direction, to construct a 3D volume from these 1D beams. The most common field that we look at is reflectivity, which is the intensity of the return pulse, that measure of shape or size, really, that we have. And it's given in units of dBz. It's a decibel or a logarithmic scale relative to a reference value. And the higher values on this scale means we have larger size. This is way too small to actually see, so I'll just let you know that the smallest values shown in this plot, which only show up in these really light grays, are negative 30 dBz. Once we start getting to the blues, we get to 5 to 20. That typically indicates light cloud formations, sometimes very light precipitation. 20 to 40 are typical rain-like values, but certain things like intense snow or dense clouds or other things can also reach up to these values. Once we get to 40 to 50, that's when we start getting into heavy precipitation. And 50 and above is either extremely heavy precipitation or we start talking about things like hail. So there's also limitations though with this. Of course, no system is perfect here. So limitation is that, again, this is only one parameter that's a function of multiple physical quantities. Even though we can generally think of, for meteorological things, of it being just a function of sort of, for normal reflectivity, we talk about horizontal pulses. We'll get into a little bit more detail on that later. But these horizontal shape, the width of particles or of objects, it's only one quantity though. So if we get birds coming in the way, birds have a different way of reflecting this radiation. So we can't say that, oh, a very large bird or a bunch of large birds are going to have a particular value of reflectivity. There's a lot of things that go into it, so there's very much an approximation going on here. There's also limitations because each of these, you see, they're little pixels or cells. A radar is just sending out a certain beam of a certain width. And because of how its pulses are separated, that also determines how far in distance each chunk is. It's essentially taking an average of everything over that volume or that cell that's detected. So it's not picking up on individual particles, it has to represent an average. So when there's a lot of different kinds of objects in a particular volume, all of those get averaged together, which again is something that has to be kept in mind as a limitation. It also, because again, we're sending out certain beams and we have to wait for them to come back before we can essentially trust that we can scan the next beam width over, that limits the amount of time that it can come back as a maximum distance that's detectable. So there's a certain range limit as well. So next product, we'll talk about the other common thing on the flip side of reflectivity is velocity. And this is a measure of the velocity or just positive or negative speed. Speed's technically just an absolute quantity, so you have to still say velocity. So it's the velocity scatters towards the radar or away from the radar location. And so not anything in the perpendicular, can't detect the full vector wind, just towards and away from the radar. And it's very useful for picking up on things like rotation. So when you have a particular cell that has a bunch of velocities going, say, away from the radar, and a bunch of velocities going towards the radar, what that means, if you have velocity going like that, you can do the whole pencil trick. That if you have going away and towards, that means that the air in between and going around that circulation has to be spinning, which is a rotation signature, which will show up as very important when we talk about severe thunderstorms. It also, if you have broad regions of high velocities, either towards or away from the radar, as long as your system's oriented properly, that means that you have strong wind speeds. Of course, sometimes your strong wind speeds are going perpendicular and the radar isn't picking up on it at all. So again, that's our primary limitation of velocity, is that it only picks up on parallel to the beam velocity rather than perpendicular. Also, we have sort of those same cell averaging and range constraints that we have with reflectivity. That's just the nature of the instrument. And there's also this additional limitation called aliasing. You can go into the details of the signal processing involved in all of this. There's mathematics behind all of it. The important thing for us to know here is that there's a certain limit to the maximum velocity that can be detected by these pulses, just by the very nature of how the signals work. That if the velocity that's being detected is actually too high, it will look equivalent to the radar signal processing as a velocity that's negative on the other. Basically, it folds over, it overflows. So it looks, instead of looking like a really strong positive, it'll actually look like a negative velocity. So this is something that can be accounted for a little bit in sort of de-aliasing algorithms, and this is usually applied to the fields that before we see them, but it can be a cause for error, and it's definitely a limitation in using these kind of data. So the last thing with radar is I was talking about horizontal pulses a lot. Let's see if I can get this animation running. Nope. I guess my animation isn't running, so I'll have to demonstrate. But typically, when the radar sends out a pulse and receives it back, those have traditionally been horizontal pulses. In about the last decade, the US's radar network, NEXRAD, recently was upgraded to both be able to alternate between horizontal pulses and then vertical pulses to come back. So instead of just getting an idea of the horizontal, the width parameter of size, you can also detect a height-like parameter of size. So you can sort of get a cross-section area of the object. And well, of course, it's not perfect because, again, averaging over the cell, it gives a lot better idea of the types of objects that are in a particular radar cell. An example of this that I'll be showing later on in the course is called correlation coefficient. Maybe that's a fancy term, but what it essentially does is it measures how similar that vertical and the horizontal pulses are that are returned, which gives you an idea of how similar or different the different particles that make up a cell volume are. And very low values of this indicate things that aren't meteorological. They're debris. So this is a very important tool for helping to confirm if an active tornado is on the ground. And we'll be talking about what that looks like in detail later. Now we go to satellites. So instead of these instruments on the ground, radars that are just sending out radiation and then receiving it back, satellites instead are instrument packages that orbit around the Earth. They're way up in there in some kind of orbit. There's two main sensing types. So there are active ones that behave. They're pretty much just radars that are flying around in orbit. They're spaceborne radars. But the majority of these that we use for day-to-day meteorology are passive. So instead of sending out their own signals, they just rely on radiation that's emitted from the Earth or that's reflected, that comes from the sun, bounces off some surface on the Earth or in the Earth's atmosphere, and then is detected by the satellite. And there's a lot of different orbit types that satellites in general can take. The one meteorological satellites typically are of two types: geosynchronous orbit, where essentially it's orbiting at the same rate as Earth's rotation, so it's always above the same location on Earth. And there's also polar orbiting, which allows it to take consecutive even scans, essentially, of the Earth's surface over time. And there's multiple detection frequencies. So we have, for active satellites, or spaceborne radars, they can send out these radio microwave frequencies and then detect them back. Our passive ones, though, typically rely on infrared and visible. And various frequencies within that, especially within infrared, that respond to certain gas constituents of the atmosphere based on their unique spectral patterns. And since they have these unique signatures, we can take advantage of that to particularly emphasize those constituents, which becomes extremely important for water vapor. So GOES, or the Geostationary Operational Environmental Satellite, is the most commonly used day-to-day forecasting tool when it comes to satellites in the US. There are similar satellites to GOES that are around the equator in geosynchronous orbit that are used by other countries, but the two GOES East and West that are used by the US fall under the GOES name. And these, again, are critical for severe and hazardous weather. So you'll be seeing me use these types of figures a lot. The ones that are currently in use, the recent upgrades from GOES 16 and 17 and 2016 and 2017, there are currently 16 different frequency detection bands going all the way from blue light through red light, a bunch of different infrared channels, all the way from shortwave infrared, where it's really close to the visible spectrum, through long wave infrared. And again, it's kind of hard to see, but some of these pick up on ozone in particular, or water vapor, emphasized in different levels of the atmosphere, or CO2. And you can also combine various bands together in different patterns to get composite plots. A lot of times what you see from satellites are true color plots, which you may notice there's blue and red, but there's not green. So we actually get green by taking the vegetation signature, inverting it, and treating that as a proxy for our green variable to construct something that looks almost exactly like what you would see with your eyes or with just a camera at the satellite's location. So to finish this up, I'm going a little bit long on time, it looks like. Just to show an example, visible allows you to see lots of really clear details, especially in these most recent GOES satellites that have high resolution updates. And you can see a lot of details. You can see shadows, you can see detailed cloud formations, but because this is visible light, you can't see it at night because the sun isn't shining to light up all of these cloud tops and the ground surface. So the other product that we use a lot, and you saw all the different frequency bands for this, depending on their application purpose, are infrared. Now these are just relying on emitted based on the emission patterns of cloud droplets or the ground surface. And these are essentially a measure of temperature, because infrared emission in the long wave is a function of the temperature of the object. So cooler temperatures, here represented in this green, are colder, which in the atmosphere, because temperature tends to decrease with height, indicate higher clouds, versus warmer temperatures as we go from in this color table from greens to blues to purples to whites to black, we end up getting warmer and warmer temperatures. So that wraps things up for this week. As far as lecture video goes, the discussion post reply, where you're commenting on an additional fact found in one of your classmates' figures, that's due on Saturday. The quiz was extended to Sunday due to my delay in getting these lecture videos up. And then next week, we're going to be talking about scales of weather. Now that we sort of have a foundation of the local properties from the first week, local properties of the atmosphere, this week getting an idea of how we look at the atmosphere through maps and measurements. Now we're actually going to talk about the big picture systems and scales of weather, so that the week after that, we can actually start talking about the focus subjects in this class, severe and hazardous weather phenomena. So I will see you then, and good luck with finishing up the discussion post reply and the quiz. Thank you.